Okay, so what I wanted to go over today is in more detail about how to do specific heat calculations so y'all can do a specific heat experiment tomorrow. So if you would like to read more about this, this is in chapter 1.11, the section on temperature, heat, and energy in your textbook. So if anything doesn't make sense by the end of the day, you can go read a little bit more and do some more of those problems, and it should be ready for class tomorrow. Okay, so just a little bit of a recap. We talked about this on Friday, which feels like forever ago. Temperature is a measure of how hot or cold an object is. And heat is the flow of thermal energy between two objects. So it's like 38 degrees outside when you walk outside and you feel heat because you've absorbed the heat from the sun. So the heat is a transfer of energy. Heat is the flow of thermal energy. And energy is the capacity to do work, often defined as the sum of heat transferred or work done within a chemical reaction. And there's 3 units of measurement. And it's important to know that there are 3 and not just 2, because 2 of them are pretty much the same word, but they have a very different meaning. So energy can be measured in calories with a lowercase c, which is typically what we're talking about in the chemistry setting. Calorie with a capital C is what's on the back of every food product label. So when it's like this can of Coke has 100 calories, that's calorie with a big C. And then joules, abbreviated with a capital J. This is another, the formal measurement of energy that we'll become familiar with today. Okay, so here are the conversions between the 3. So 1 calorie with a capital C is equal to 1 kilocalorie or 1,000 calories. So all of those 3 things are equivalent. 1,000 calories is equal to 1 calorie. 1,000 calories is equal to 1 kilocal. 1 kilocal is equal to 1 calorie. Is everybody cool with that? So you can do that math. So again, the food calorie is a capital C, and anything else with a lowercase c is going to be what we often use in like the chemical textbook. And 1 joule is equivalent to 0.2390 calories. And then again, if you're kind of converting back and forth between them, 1 calorie is equal to 4.184 joules. 1 kilocal is equal to 4.184 kilojoules. So see here we've got joules and calories, and here we've got kilocalories and kilojoules. But the numbers stay the same. This is one of the reasons why I work with the prefixes. Because instead of writing like 1,000 is equivalent to 4,000, or yeah, 1,000 would be equivalent to more or less 4,000. But so these are all the conversions. Did y'all get a conversion handout? Does it have any of this on it?
You should have gotten a conversion.
You got a conversion handout.
I'll have it.
Awesome. So this is the thing, you don't have to memorize it. If you use it a whole lot, you might eventually memorize it. But you should have this written down on a conversion sheet. Awesome. Is this one right here? Beautiful. Is it on there somewhere? Energy, yeah, in the energy section, these conversions are written down for you. Cool. 1 cal equals 4.184 joules. Cool. Any questions about the conversion so far? We're going to be working with these numbers a decent amount today and tomorrow. Okay, so here's our first math problem. So try to do it on your own and then compare with your neighbor, and then we'll go over the answer together. So how much heat in kilojoules is released when a 400 calorie capital C hamburger is consumed? So show your work and then compare with your neighbor.
Sure, it's 4.4. That's the one that's 4.1. So yeah, 1,000. Stairs?
Yes. Yes, so this one here, the common to like 401, I would go, oh, this is like, here's an instance where like four.
Feels like 2,000. Going from 1,000. You're going from 1,600 to 2,000. It's like least.
So, if there's a slide, Friday, zeros after a number, zeros after a non-zero number are unclear. So it's like it's 400, like we're certain 400. Yeah, it could be like 400.01. It should have been, I should have made it different. But we're good.
So whenever it's like that kind of number, just always have that.
I would say,
Because like, yeah, 1,673, it's all 2,000.
there's a big difference there. You gotta show the so probably focus more on huge, like, if there were 6 numbers, all the ones that are clear. Kind of like the lowest one. Yeah, cute. Excellent questions. Okay, do y'all want some more time to work on it on your own, or do you want to see the answer solved? More time. You're welcome. What's the question?
Should that be a capital?
No, it's a lowercase c.
Right above it, lowercase c.
So basically, there's no K here and no K here, and there is a K here and there is a K here.
Above, like, look, it says lowercase e is the same. It's 0.239. And then right below it, it just says 4.86 joules. Because you're converted. That's a joules to calories, not calories.
Nah.
Calories and joules, calories. So if you have 1 calorie, it would be way bigger. Oh.
Yeah, there you go.
What am I doing?
It's okay. Math is complicated. Got it.
Well, yeah.
So you're getting it? More time, you're good. Okay. Okay, so there's a lot of ways you can do this. So there's multiple ways you can do this. We said earlier, there's 1 calorie in there's 1 capital C calorie in every 1 kilocalorie. So 400 calories is equal to 400 kilocalories. And then we're going to take that 400 kilocalories and multiply it by 4.184 kilojoules per kilocalorie. So we get 1.63 times 10 to the third, or 1670 kilocalories. And so one of the things, did everyone get this and or this rounded? Awesome. So basically what we talked about very, very briefly last week, zeros after a non-zero number, when they're not in the decimal place, these are unclear. So it's unclear if this has 1 significant digit or 3 significant digits. And so usually in this case, when a number has an uncertain, unclear amount of significant digits, you can stick to all the ones that have a very explicit number of significant digits. So here, this one, but this could be 3, it could be 1. So if you went with 3 significant digits or 1 significant digit, those are both fine answers. Again, we could be like roughly 400, roughly 2,000, or exactly 400, exactly 1.67. Did anybody calculate it differently but still get the same answer? Yes, how did you do it differently? Nice. Anybody else do their math like in a different order of operations but still get the same answer? Did anybody get a wrong answer and they want to know maybe where they went wrong? Awesome. Okay. So one more thing. So one thing that really helps me when I'm grading is if you put a box around your answer. I don't know if that's a thing that y'all had to do in math. Did y'all have to do that in math? Yeah, so especially when you're working out like a really long problem, especially if your problem kind of like spans multiple lines, if you can put a box around your answer, it makes grading a lot easier for me. And when the grading's easier, then like life is just better and I can just like, yes, yes, versus having to like look really hard for your answer. Okay. Let's do ones. Okay. Okay. So we'll have a little bit more definitions before we move on. So the specific heat of an element or of a metal or like a mixture, the specific heat refers to the amount of heat needed to raise the temperature of 1 gram of that substance by 1 degree Celsius. But heat capacity refers to the amount of heat needed to raise the temperature of some quantity by 1 degree Celsius. So like when we talk about the heat capacity of the lake, we're not talking about like 1 gram of water, we're talking about the whole lake. How much heat would it take to heat the whole lake by 1 degree? That's why it's like not done instantly. Like that requires a lot of heat. But the specific heat to raise 1 gram of a substance, these are known, they're called constants. Some scientists back in the day figured it out. They took 1 gram of all the elements, of all the main substances, and tried to figure out how much heat it took to raise them by 1 degree. And water is a constant that we're going to use over and over and over again in a lot of our equations. And so water, again, this is like a fact that you don't have to memorize, but it's on your sheet. And this constant comes into play a lot when we're working with specific heat. So the specific heat of water is 4.184 joules per gram times degrees Celsius. If you're working with a different substance like iron, which we'll do in the next on the next slide, it has its own specific heat. But this is the one that we use for this number will sound familiar. Hi. You're welcome. Is this for today? It is, yes. This number is the one that we used in that conversion of joules to calories. So that's why it seems familiar. Yeah, okay, cool. Any questions about this page so far? Got it. Okay, so there's a table. I showed you this table briefly. So almost every substance has been measured. Its specific heat has been measured. So helium gas, it takes 14 joules per gram per degree Celsius. That's its specific heat. So 14 joules to heat it up 1 degree Celsius. You don't have to write it down. This is a reference, like a chart for reference. And it gives you a good idea though, as you change states from liquid to solid to gas, each of those physical states has a different specific heat capacity. Yes. Back one side, sure thing. You can print a couple more maybe. Yes. Yes. Okay, so again, this is a table made by some scientists. One of the cool things about science is a lot of people are very like open source. They're like pro sharing of data. So this is out there. You can Google it. It's in your textbook. But yeah, so all these measurements are out there so that you can use them without doing this. But I think this is essentially what you're going to do in lab tomorrow is test this specific heat capacity of different substances. So you'll be able to confirm or their answers. If you get a different answer, I feel like these have definitely been confirmed by a lot of people. So maybe if you get a different answer, it'd be good to look into why you got a different answer versus maybe challenging the published data. But that's fine. It's always good to question other people's results in light of new results. Okay. But yeah, so definitely there is, so ice and steam actually have the same specific heat, but that's a little bit different than water. And let's see if there are any other cool ones. I think we're good. Okay. Okay, so this is like our main equation that we're going to work with today and tomorrow in lab. So Q equals NC times delta T. Are y'all all familiar with delta, the triangle? Yeah, so delta means change in. So this is, so Q stands for heat energy. M stands for mass. C stands for the specific heat capacity. And delta T stands for change in temperature. So in order to solve, so when you, with working with these equations, for the most part, you'll be given 3 out of the 4 things, and you'll have to solve for the 4th. Maybe you're given the energy and you solve for mass, or maybe you're given the mass and you solve for the energy, something like that. But the specific heat capacity will come from that previous slide. It's like a known quantity that you can look up. So if you aren't given that, then you can Google it or you can look it up in a table. It may not be explicitly provided in the question, but it is specific, it is a known thing. I'm wondering if that is on your equation. Sure. Oh yeah, it's the very top one. Apparently it's important. Okay, so here's our word problem for the day. I know. So basically this is, okay, so one thing, when you're reading word problems, like if anybody goes to take, you go to take the SAT or something, a lot of times there's a lot of words in the word problem, and your goal is to hone in on the key pieces of information that you need. So how much heat in joules must be added to a 5.00 times 10 to the 2 gram or 500 gram iron skillet to increase its temperature from 25 degrees Celsius to 250 degrees Celsius. The specific heat of iron is 0.451 joules per grams per Celsius. So given this equation, energy equals mass times the specific heat constant times change in temperature. How much energy do you need to heat up a pan so you can cook yourself breakfast? Oh, yay. Do you need one today? Okay, yeah, perfect. Correct. Yes. And it's heating it up, so it should be hot. Like we're cooling it down.
Yeah, that's what
We're trying to do. So it needs to change 225 from 0. Get back to 0.
Yeah.
Yeah, that's like so we maybe that's $5. That's how it's right. It's like joules per gram. So then you have this right? So you get that all out of the sun. Well, yeah, that's fine. No, yeah. So, yeah. Okay, so no, it's 500 times.
Rounding down. Wait, it's just Is it grams?
So we were.
You subtract the lowest one from
Wait,
satisfaction.
Yeah.
Somewhere in there.
Yes. So you're kind of missing all your units. You have
Oh,
your
yeah.
units problematic. Yeah. Just saying. It's already in Jules. Yeah, it's already in Jules because we were given this in Jules.
So what if we?
Yeah, you don't have to do anything for something. Yeah. A trick question would be to put it in kilojoules and ask the answer in joules or to give it a thing.
Then that would.
Then you have to convert to it. There's no conversion.
Oh.
Yeah. Yeah.
I know.
You don't need any conversions though.
For the last problem.
For
somehow I got 1.6.
this one or this one?
Yeah.
So 1 calorie is the same as it. Correct. 1 capital C calorie, like in food.
Oh, okay.
Yeah. Yeah. Good?
Yeah, I got it.
Okay. Okay, you want some more time or you want to see it solved? Okay. Okay, actually, yeah, there's a couple people we'll work because I think I've seen a couple different answers. Okay, so we're gonna start with 500 grams. So definitely when you're doing these really long equations, keep your units there. So 500 grams or 5.00 times 10 to the 2 grams times 0.451 joules per gram per degree Celsius times 225 degrees Celsius. I got 407. Did I get it wrong? Let's see. What did y'all get? 507. Someone had 2 more zeros. Did anybody get 507? One person? Okay, we'll have to do some math real fast. Is there a calculator up here?
Usually one.
Okay, so who wants to explain their answer? We'll figure if we got the wrong one or not. Yes.
So I put in Google 500 times 0.451
Uh-huh.
times 225, and it gave me 50,737.5. That's what
Oh, I think this should be like a kg. This is what, yeah. Okay, so,
Here's your calculator.
okay, I think, yeah, I have a feeling y'all are right. So if we make this, oh, it won't let me edit it, huh?
Most of them are the exact format.
Yeah, okay, so the other way to do this. Ha ha ha.
5.07 times 10 joules.
Oh, weird. Why won't it? Oh, I know it's wrong. Okay, there we go. So, but it does want it in joules, so, right? Okay, this is where y'all are right. Yes, ma'am. Nice. Okay. Cool. Okay. So yeah, I feel like I must have like copied and answered those in kilojoules and not joules. But anyways, okay. So one thing I've noticed, you when you're doing your equations, definitely put your units so that you can cross them all out to make sure that you're ending up with the right answer. So these grams cancel out with this gram on the bottom. This degree Celsius cancels out that degree Celsius, and we're left with a joule. So 50,000 joules or 507 kilojoules. Okay, did everybody get 50,000 joules? More or less? Awesome. Okay, and then so just written out, if you want to write this down somewhere, delta T, or the change in temperature, is your final temperature minus your starting temperature. So if you're heating up a substance, your delta T will be positive. If you're cooling down a substance, your delta T will be negative. Cool. Any other questions? Oh, is there one more? Oh man, okay, I got one more. We have time, right? 30 minutes. Oh yeah, we have plenty of time. Okay, good. This gives us a chance to look at some of the lab stuff. Okay, so here's, oh no, the answer shown. Okay, so if we have a flask of water containing 8.0 times 10 to the 2 grams of water, if it is heated and the water changes degrees from 21 to 85 degrees Celsius, how much heat did the water absorb?
Oh wait, you already have the.
You want the heat capacity for water? 4.184 from your previous equation, yeah. Yeah, so see, that's what, anytime you're not given a specific heat constant, they just want you to look it up. Oh, it's right here. Yeah, so we have it. It's not like, let me back up so you can see it. 4.184 joules per grams times degree Celsius.
is 200.
The specific heat of water, what was it again, 4.184 joules per grams degrees Celsius. There are only 2 significant digits on all of them, so yeah, you can have so 21 is too big of a first number. It needs to be between 1 and 10. So 2.1.
2.1 okay.
Yes, let's put the answer in joule.
It's 200,000, not 21.
Can you joules, or it doesn't say, so you can do joules is the easiest. If it's a really tricky number, you can do smaller number. Oh. So serious. Sure. That's a start. Asked her to cover it because it was with you. Oh.
Why'd you not do 2.14?
Oh, every sheet, file. Radio. Nice, there you go.
honestly, I can't see every single dish. This, that's the most information.
Okay, does anybody need any more time on this problem? Does anybody want to do it on the board? No, I know, it's scary doing it in front of people. So what are some answers people got? Yes. 2.1 times 10 to the 5th joules. Everybody else get 2.1 times 10 to the 5th joules? Beautiful. Why did we pick two significant digits?
64.
All of these numbers had two significant digits, so we're going to report our final answer with two significant digits. The answer didn't specify whether to provide the answer in joules or calories or kilojoules, so you can choose whatever format you want as long as it's correct. But the one that requires the least amount of conversions is going to be the one that's least prone to error. Cool. Okay, so for tomorrow's lab, so you're all cool with these specific heat calculations? So basically tomorrow, you're going to be putting some things, copper into a water bath, heating it up, watching the change in temperature and figuring out how much heat you gave to it. So you'll need to know the specific heat of copper. Okay. So basically, I didn't print it out yet, but hopefully you can print it out tomorrow. There'll be a procedure that you'll follow, and there'll be a report that you fill out, and you'll upload the report to Canvas. If you don't get finished on tomorrow, you'll have a little bit of time on Tuesday. And then, so basically, I'd like for you to be done with one lab before we start the other one, but it will be available for like a whole other week after that. So if you need more than a whole more week, then like come talk to me and we'll figure out like why it's taking so long. I think that's all for now. Anybody have any questions? We do have some time left, right? I think we have some time left. So what I would do is we're going to try to troubleshoot some of the Canvas things that we've been having.
So I have a solution.
Yes.
So you guys, can everyone listen for a second? Your lab 3, you have two things you need to upload. You need to upload your Excel sheets. So all those sheets you need to upload. Okay, and you also need to upload your data sheet that you're writing on. The report. Okay. You can do this in 2 ways. Okay. Here's the way I would recommend. You can do 2 attempts. So, well, actually, I should ask you, Dr.
Yes,
So
I'm fine with multiple attempts.
first attempt would be their Excel sheet, and then their second attempt would be their data sheet. Is that okay?
Perfect.
You guys could also print your Excel sheet out and then cam scan everything, all your Excel sheets and your data sheets, and then just upload once. It's really up to you guys. I think either way would work. You would still be able to see everything.
And then the final way, if for whatever reason you already uploaded something and it won't let you upload something else, you can Canvas message me a PDF.
It should, because it's unlimited attempts.
It's unlimited attempts.
So it should not limit. I mean, try not to do like 6 attempts. That probably gets really confusing. for you. But try to do it in 2 attempts, I would say.
Yeah.
If anyone needs help with that, please let me know. If you guys need help figuring out how to get your Excel sheet, can I show you guys how to do that really quick?
Yeah, let's do a little attempt.
Do like a random Excel. Actually, I might have an Excel. I could just
Pull up.
show them.
Yeah, there you go.
Yeah, thanks. Sheets. Oh, Milan shared hers with me, right? Who was that? Who shared that with me? That would have been.
Oh, that's so fun. That'll still work.
I'll just add another sheet like some
Okay.
data. So.
Awesome.
Dude, I go so low, it's like the back of my house.
Okay. So, can everyone look up here?
Yes, Tom.
So thank you. So if you guys look here, here's like some random info. Let's say you have your sheet, obviously, right? But if you go to File, so you're able to upload, go to File, go to Download, go to PDF. But here's the thing you have to do. When it says current, because you have multiple sheets, a lot of you have multiple sheets on the same sheet, right? I don't want just the first page. I want like 3 pages or 4. You guys like have like 5 different sheets. So instead of current sheet, go to workbook. If you select the entire workbook, then it'll print it on each page. So here's each page. I don't know why there's so many for this one. I don't know what happened there, but you guys shouldn't get like a million like this. It should be 4 or 5 or whatever you have. Then you're going to download that as a PDF onto your Chromebook or whatever device you have. You're going to upload that as your first submission. And then you're going to cam scan all your data sheet, and that's going to be your second submission.
We're going to have 2 submissions.
You should have 2 submissions. If you want to have 1, you could print this out and then scan everything. You just have 1. So that's your other option. Whatever works okay for us too. Does anyone have any questions on that? No? Yeah, okay. Yeah, actually, communication by hand.
Oh my gosh, that's so cool.
It's good. Make it do it. And then Excel will do it. Now they actually know
Know what it's doing. Next year.
Yeah, next year.
Next year.
Okay.
Okay, does anybody want me to come around? Raise your hand if you need to chat with me. Otherwise, y'all can keep doing what you're doing. We got like 5 minutes left. What's up? 3 minutes? Yeah, you're good. Awesome. Yes. It'll be Sunday. This one, yeah. You should have almost finished it in class. So if you finish it in class, you figure it. But Sunday night. Yeah, so. Apparently I gave it to you. My bad. That was really complicated. You're probably not quite there yet.
motion, I say that. I'm like, you gotta cover your like,
Yeah, so this will make more
and
sense.
6 bars.
Yeah, and hopefully after today.
And there will be like 5 minutes.
Yeah, this will make more sense. Yes, so. All good?
We're just like,
Yeah.
bruh. You know what is progressive? There's like
Oh,
like,
yes,
this is like a
Yeah,
perfect example.
no, it's not.
Like, he's the only one that's not an ass. Maybe if we're just, let's be optimistic, maybe everyone should. I don't know what is yours. But she too. Great, now my
That's the big three. You go ahead and do it.
Okay. That way it's affordable at a like hours. Yeah. It's just come in like and then you kind of this part.
Why not?
No, stay away from those guys. Stay in here.
What's the worst?
I highlight all of it.
Oh, it's okay. It's okay. Google saves everything.
Great, look, it just changed all of the pictures. Look at its alter. Just you can hit that back button.
Control Z.
Is that it?
Yeah.
Okay.
Just
Just promptly.
that's why I
Promptly select